One of the most common questions I get from students is why? Why do we have to learn this? Why are we torturing ourselves with linear algebra? And aside from the canned answer that math helps develop the ability to follow protocol, and critically think, and solve problems, linear algebra forms the basis to many, many tools and techniques that are used daily by data scientists. So I'm going to try to give you a little glimpse of this by just browsing some Wikipedia articles. The first for principal component analysis. And we'll find that it starts talking about, real coordinate spaces and spaces and an orthonormal basis and a change of basis, dimensionality reduction and eigenvectors for covariance matrix, the singular value decomposition. These are all words that if you don't know linear algebra, they're beyond your scope. And by the time we get through the MSA linear algebra, we'll be able to read these paragraphs and understand just exactly what's going on. Another one might be factor analysis. If we scroll down with factor analysis, we see it states in matrix notation, x minus m is just matrix multiplication. So many of the most important techniques in data science are just matrix multiplication. But the key to understanding them is understanding matrix multiplication inside out and backwards. Now we'll end here with k-means clustering. Right here we see some bold letters. Why are they bold? Well, because they're vectors. And then these two vertical bars, that's a norm distance that we'll talk about in the final lecture. So without further delay, we won't be able to talk about these applications today. These applications we will get to in the MSA program, but we'll start with some of the more basic applications in systems of equations.
Okay, so now let's talk a little bit about applications of matrix multiplication. And this is just a quick introduction to give you an idea why we perform matrix multiplication the way that we do. And the main application that you'll see is with systems of equations. So matrix multiplications that occur with a set of unknown variables creates a system of equations. So for example, here I have a matrix A, a vector x that has some unknown quantities, x1 through x4. And I have a vector B that has some known quantities. So if I look at this matrix equation, AX equals B, I'm multiplying A times X. So I'm multiplying every row of A times X. So if I think of what that's going to look like, the inner product would be x1 plus 2x2 plus 3x3 plus x4. And now I'm saying that's equal to B. So that's going to equal this first element in B. So that's this first equation here in this system of equations. So a system of equations is just a set of equations that are simultaneously true. So we're saying that all three of these equations hold true for these unknown values. So we'll need to learn to go back and forth between systems of equations written this way and systems of equations written of the form AX equals B using matrix notation. And these systems pop up in all types of data applications, anywhere from regression analysis to optimization. So let's take a look at this. Just some very basic stuff. So here we're dealing with a manufacturing company that makes trail mix. And they make 3 versions of their product. One for airlines. It's not a particularly good kind, as we've all been on airplanes. One for grocery store, and one for gas stations. And so each of these versions has a different mixture of peanuts, raisins, and chocolate, and they serve as the base of the trail mix. And the base mixtures are made in 15-kilogram batches, and they're sent to a second building for packaging. So we have some information about these mixes, and here the rows of this little table here represent the different types of batches. So the airline mixtures is mostly raisins. The grocery store mixes are mostly chocolate, And the gas station mixes, again, are mostly raisins, a little bit more peanuts. And we know about the manufacturer's storage capacity for each of these types of ingredients. And we also know how much these ingredients cost to purchase per kilogram. So using this information, let's look at some of the types of information that we can use linear algebra to get. And always keep in mind when we're doing these examples, this one looks like it fits nicely on a slide, right? But most of our real data problems are not going to be 3 by 3 tables. They're going to be very large. And so these computations may seem like you can do them by hand, but when we get out there in the real world, we will not. Okay, so to start with, if we want to use up all the ingredients in storage each day, how many batches of each mixture, airline, gas station, and grocery, should we make? So if I want to use up all of this storage capacity, how much of each mixture should I make? Well, we're going to set this up as a system of equations, and we'll have one equation for each ingredient. We're going to let A be the batches of airline mixture, G be the batches of grocery, and S be the gas station mixture. All of these things need to be greater than 0 because I can't produce negative batches of a mixture. Okay, so looking back at the table here, A, G, and S. So if these are the kilograms per batch that I use for raisins, then 7 kilograms times the number of batches of airline plus 2 kilograms times the number of batches of grocery plus 6 times this S, that summation needs to be equal to 380. So 7 times A plus 2 times G plus 6 times S should be equal to 380 if I want to use up my entire storage of raisins. Similarly, I would do the same thing for this column. 6 times A plus 5 times G plus 4 times S. So this pattern of doing these almost inner products with this column of the matrix and these variables is exactly what we mean when we do these systems of equations. So I have one equation for raisins, one for peanuts, and one for chocolate. These coefficients here come from the columns of the matrix, or the table, I should say. And these right-hand side values come from the storage capacities. So now we can transform this system of equations into matrix form. And we simply have the matrix of coefficients multiplied by the vector of unknowns. And we know that the right-hand side vector are these supply capacities. And so we haven't yet discussed how to solve a system like this. We can verify just by multiplying through that this solution listed here, A equals 20, G equals 60, and S equals 20, is in fact a solution. But we don't know yet how to tell if it's the only possible solution. And that'll be the subject of the next block of lectures. So once we transform the system into matrix form, AX equals B, here's my A, here's my X, the vector of unknowns, and here's my B, my right-hand side. A good question to ask would be, does the matrix A have an inverse? Because one of the reasons an inverse might come in handy is that we can multiply both sides of this equation by the inverse of A. So if I were to do that, if A even has an inverse, so again, we never can just go multiplying by inverses. We must first show that a matrix has an inverse. But if I can show that, then I can multiply both sides of this equation by A inverse. And you'll notice here that A inverse times A, that equals the identity. And the identity times anything is that thing. So the identity times X is just X. So here is a quick way for me to solve for the unknown vector X. So if we know the inverse of A, then we can solve this problem by simple multiplication. However, you must be very careful not to assume that a matrix has an inverse. And, unfortunately, we don't often deal with situations where the inverse matrices do exist. Okay, so going back to our example, let's talk about how we might use matrix vector multiplication to determine how much it costs the manufacturer to produce one batch of each mixture. So again, we knew the cost of each ingredient. It's $2.55 per kilogram of raisins, $4.65 per kilogram of peanuts, and $4.80 for a kilogram of chocolate. So all we need to do is compute this linear combination of the cost times the kilograms of raisins, the cost times the kilograms of peanuts, etc. And we need to compute it for each type of mixture. Well, anytime what we're computing is a linear combination, matrix vector multiplication makes this very easy. So looking back at our table, these are those cost vectors we just came by. And so now for each row of this matrix, I want to multiply the row times the vector down here for cost. So it would be an inner product of this vector here, this airline row, and this cost vector here. Because if I multiply the cost of raisins times the kilograms of raisins, cost of peanuts times kilograms of peanuts, cost of chocolate, kilograms of chocolate, what I'm going to get is the total cost for the airline mixture. And then I want to repeat that for the other two rows of the matrix. So, if I take the data table just as it is, this is the first row of the data table, the second row, and the third row, and I multiply it by that cost vector, what I'll get is the cost of producing the airline, the grocery, and the gas station mixtures, respectively. So, just putting this information into a table, here I've figured out the cost of each type of mixture using a matrix vector product. Okay, so moving away from that example, another thing that we should talk about is, so we've only focused so far on matrix vector products, but we should also talk about matrix products. With matrix products, the systems that we generate get very large very quickly. We'll just take a 2x2 example. Now I have a capital X of unknowns, so I have a whole matrix of unknowns equals B. So when we think about this, what this means is that I'm going to multiply the first row of A times the first column of X to get this 1, 1 element of B. So this vector 2, 3 times the column vector x1, 1, x2, 1 will just be this inner product, and I have a right-hand side equal to 7. So for each row times column, I have a right-hand side value in B. So I have as many equations here as I do elements in B. So here, with a 2x2 matrix multiplied by a 2x2 matrix, it equates to 4 equations with 4 unknowns. One for each entry in the right-hand side B. So obviously, as matrices get bigger, the number of equations in the system when I'm dealing with a matrix product are going to multiply very quickly. It's not often that we see these, but we will come across them in factor analysis and principal components analysis. So what we really want to get to is regression analysis. And so regression analysis is in fact a system of equations. So let's consider a regression where we have some dependent variable, y, and 2 independent variables, h and w, say height and weight. So our goal is to find these unknown parameters, the beta 0, the intercept, the beta 1 and beta 2, so that y, our target or our dependent variable, is equal to beta 0 plus beta 1h plus beta 2w. Now, when we look at this single equation, our data is never actually referenced in here, right? We want to run a regression analysis on a data table, but we don't actually make reference to that when we talk about the equation. So where does the data fit in? Well, suppose that we have just 4 observations, and they're listed here in this table. Well, when we write this regression model, the y equals beta 0 plus beta 1h plus beta 2w, what we're really saying is that this equation holds true for each of the 4 observations in our data set. So rather than one single equation, how we always represent it up here, what we really have is 4 equations going on in the background, one for each observation. So these values filled in here are the heights, the weights of the observations, and the y, or the target variable, of each observation. So we're going to have one equation for each observation. Now, we know from experience that these equations are not going to hold completely. There is no solution, beta 0, beta 1, beta 2, such that all of our data is exactly mapped to the target variable. So again, rather than writing out all these equations, we'll represent the situation in a matrix format. So here we have our matrix of coefficients. And you'll notice this comes from the previous slide, the previous system of equations, where the beta 0, the intercept, is in every equation, and its coefficient is always going to be 1. So our data matrix will always have an extra column of 1s to represent this intercept, and then we'll have the variables that we want to use in the regression. So this is the variable height, and this is the variable weight. And so if I multiply this coefficient matrix by the vector of unknowns, the vector of betas, what I'll see is exactly this system of equations. 1 times beta 0 plus 3 times beta 1 plus 3 times beta 2. And I want that to be equal to my target variable, y. So in a very compact format, we're writing our regression equation as x times beta equals y. Even more compact than the regression equation that we write out here. So when we see this x beta equals y, what we should think is the system of equations that's going on in the background. So like I said, we do know from our experience that data in this situation will not have an exact solution, right? Our data does not fall exactly on some straight line or some plane. If it did, we wouldn't need data analysis. So instead, what we have to do is consider some error and try to minimize it. So rather than having x beta equals y, what we really have is x beta plus some error is equal to y. And so this error is going to be contained in a vector of the residuals. So each observation will have a residual quantity, which will be determined. And our goal will be to minimize this. And we're going to talk much more about how that's done in the later lecture. The main purpose here is just to see how we set up a regression equation using matrices and vectors. So that's all we have for this lecture, and when we come back, we're going to start talking about solving these types of systems of equations.